Okay, so let's recall what we did in the last lecture. So this is Feynman Theorem 2. So basically, in the last lecture, I stated the result like this. I mean, the simplest version of this theorem, simplest non-trivial version, is a statement like this. There are similar statements, of course. One can write exponential of minus 1 over h bar s of x dx has an asymptotic expansion in powers of h bar of the following form. So this is asymptotically given by root h bar sum k from 0 to infinity. Then there is h bar to the power 2k. Although I think it must be k, I'm not sure. Sum. Then there's a sum over graphs, W gamma over order of automorphism group of gamma. So here, gamma for this particular problem belongs to the set GK4. So let me write what this means. Okay, first of all, what is the action? So in this case, for this particular example, the action is just 1/2 ax squared minus g over 4 factorial x4. This is a quartic action. It's just one-dimensional quartic action. And what is this g K4? This is a set of isomorphism classes of 4-valent graphs with k vertices. Okay, so it's a finite set, obviously. So k here goes from 0, 1, 2, so on. For k equal to 0, we just assume this number is 1. So the series starts with 1 here. And then, otherwise, we have this isomorphism, set of isomorphism classes of 4-valent graphs with k vertices. And aut gamma is the automorphism group of this graph, gamma belonging to this set, and then, So, all right, and okay, so this W of gamma is this Feynman weight of gamma, which is defined using this A and this G and the fact that this is quartic. I will explain it. I'll mention this, I guess, in the last lecture, but I'll explain it as we go through the proof, how to get the Feynman weight of a graph. These are so-called Feynman rules in this case. Okay, I guess I explained everything. Now there is I'm not very happy about this h bar to the power 2k. We derived h bar to the power 2k, but I think it should be h bar to the power k, but we'll see. If there is a need to be fixed, I will fix it. Probably we have to, but all right. So now, what's the idea of the proof? Well, first of all, I mean, we know that there is this asymptotic expansion, r exponential minus 1 over h bar, 1/2 ax squared minus g over 4 factorial x4, right? Dx. What we do, we say that this is given by a simple expansion if we write this exponential as series and then replace summation, commute, summation, and integration. So this is part of the very general theorem from asymptotic analysis. This is asymptotically given by integral over r e to the minus 1 over h bar, and there is 1/2 a x squared, then yeah, so let me write summation here already outside, k from 0 to infinity, and this term is of course g x4 to the 4 factorial to the power k dx. So now this is down here, so it's just multiplied by this exponential. This polynomial is multiplied by this exponential, and this is asymptotic expansion like that. Okay? So this much we know. And if you look at it, so this is, so we are down to computing such integrals. In this case, integral of the form exponential of minus 1 over h bar. Yeah, a x squared, and then I've got g to the k, x to the 4k, divided by 4 factorial. Oh, there is 1 over k factorial here. Sorry. And then there is dx. G to the k, x to the 4k, 4 factorial to the power k. And then times k factorial, there is dx. So we have to show that individually each of these integrals, one-dimensional integrals, is given by this sum up here, by this part. Okay, so, all right, so, yeah, of course, I mean, this integral we can immediately compute. We know its value exactly, so we don't have to go through this. But the point of this, writing the proof like this, is that it extends to n-dimensional case and to infinite dimensional case, something that the other argument doesn't work in general like this. So now the point now is to use Dick's theorem first. Implies that this integral, so let's call this ik, okay? So ik, where k equal to 0, 1, 2, so on, ik is given by sum over, again, I use this notation, weight of gamma, but these gammas are quite different from these gammas, I tell you. So here, gamma, so this summation is over labeled one-valent graphs with 4k vertices. So in this case, gamma belongs to one-valent, labeled. All these words are important. One-valent labeled graphs with 4k vertices. So basically, in other terminology, these are called pairings of 4k vertices. So this is the set of pairings of 4k labels. So you just take the numbers 1 to up to 4k and create some pairings between them. And for each pairing, we put this number, A inverse here. And then for, and then there is this G also. So we just multiply all these things. Okay, so this is now the point is that this is a huge set. It has 4k minus 1 double factorial elements, as you can count. You did counting. This many labeled one-valent graphs. And it's in general, not for this problem, but in general, in n dimensions, it's quite difficult to write this, to use Fick's theorem directly to sum all such terms like this. So the trick that is Feynman's contribution, really, I think, I'm guessing, is not to use this Fick's theorem, but directly use graphs like this, which are much more interesting. And there is much less such graphs than one-valent graphs. So let me tell you now the trick. So I don't want to erase the theorem, so I'll just keep the theorem up there. So now the idea is to change one-valent label graphs with 4k vertices. You're going to replace summation over such things to summation over these guys to the set GK4. Graphs with k vertices. They are 4-valent, and that's it. Much smaller set than this one. And then I will define, I will tell you, well, we already discussed this in last lecture, what this W of gamma Feynman weight in this case is. Okay, so how this reduction is done? Well, as we discussed in the last lecture, the idea is this. Imagine, so how this is done. So imagine, let's take k equal to 2. So we have 8 vertices labeled, and we want to do pairings of this thing. So the idea is that we create 2-bit nodes and we connect all these things, and this one to this next set of nodes, vertices. Okay, so when you have pairings like this, you do get a graph. So this is something which is like forget about this part. I mean, this is really just a pairing of, yeah, k is equal to 2. 2 times 4 is 8 labeled vertices. But then the graph that you get by this method is the following graph. So we have 2 vertices, k is equal to 2. And if you think about it, we have this thing here, we have this thing here, and we have this here. Yes, one connecting edge like this, and then there is another connecting. Okay, now how do we use this graph to get W gamma? Well, you decorate these graphs in the following way. On each vertex, we put a G, the coupling constant of the quartic action, and then each edge we put the propagator. In this case, it's just a number, which is A inverse. And then we multiply all these things, right? So then we get A inverse to the power 4 and then G2. So this, of course, gives us one term here for k equal to 2. And that, but then there is this strange division by automorphism, or order of the automorphism group of this graph, while here we don't have. But mind you that we have to divide this contribution by something else, which is this number 4 factorial to the power k times k factorial. So yeah, I mean, so the thing that you get from pairing, you always get A inverse to the power 4 G2 for these pairings. The question is how many these pairings are divided by this compared to this right-hand side, which is quite. So basically, it's a non-trivial statement that the summation over pairings divided by this number, total number, is given by this weighted sum over graphs. That's a very, very non-trivial observation, right? So that's quite non-trivial. And why is that true? So it turns out actually this is something, if you think abstractly in terms of group theory and group action, it's a result of a very easy to understand, but still quite useful fact from group actions. So I'm going to write it in that form, and then I will tell you that all these results, similar results, follows from just one simple, basically undergraduate fact from group theories, specifically group actions. So let me write that fact now. So what is that? So I write it as a theorem. So okay, so from the outset, let's assume that G is a finite group and X is a finite set. And this X is a G set. So we have an action, say from left of G on X. So the notation is Gx goes to Gx. So we have an action of this finite group on this finite set, right? And there is also a function W, we think of it as a weight function, from X to R. And we are assuming that this W is G invariant, so W of Gx is equal to W of X for all G and X. So this W is G invariant. Okay. So having this setting, then you can turn summation of elements of W, I mean, summation of W over X, so to speak, integration of this function W over X, you can reduce it to integration over orbits. Actually, not over orbits, over isomorphism classes of orbits. So let me write it like this then. So we have, given this very simple setting, we have the following fact: 1 over order of G summation f of x, W of x, sorry, x belonging to x, right, is equal to sum. So I'm going to write it like this: W of O divided by order of automorphism group of O. Now I have to explain these terms. But O belongs to calligraphic O. So this is the set of orbits. So this is the set of orbits of X under the G action. Now, what is this automorphism of? So what is this W of O, weight of orbit? Well, this is value of W on any point on the orbit. Okay, so here is the picture. So you have this X, and you have decomposed it into disjoint unions of some orbits, right? So for each orbit, you pick an X, and then you compute W on this x, you call it W of that orbit. And it doesn't matter which x you choose because W is G invariant, right? So it doesn't matter which x you choose. The value of W on each orbit is constant, right? Okay, good. But we cannot just simply sum these numbers over orbits. We have to look at automorphism group of this orbit. So what is the automorphism group of orbit? Again, this automorphism group of this orbit is really the isotropic group of any x. So again, so this is an orbit. And so for each x in the orbit, we just look at the isotropic group of that x. So this is the set of all G belonging to G that fixes x. The isotropic group of that little element x, right? Now, if you pick different x's on the same orbit, this group changes, but only changes by conjugation. So the number of elements of the automorphism groups. So basically, any two automorphism groups are isomorphic of the orbit. So it doesn't matter which how you define automorphism group of this orbit. So now both sides are defined, right? So we have defined left-hand side and right-hand side. Now, if you think about it, this is really a beautiful formula because it just says that integration over of invariant function over this total space X can be reduced to integration over the set of orbits, but the measure on the set of orbits changes from orbit to orbit. Which measure you have to choose? You have to choose this measure 1 over order of automorphism group of this. So this is a kind of weighted discrete measure on the set of all orbits here. And the proof of this is absolutely easy, in fact, trivial. So I won't repeat here, but I highly recommend you think about it because this result has many, many applications in counting problems. I don't know what to call it, orbit sum method or I don't know. I mean, this is also related to this Faddeev-Popov method of path integrals for gauge fields that maybe we will look at it sometime later on, but that's the continuous infinite dimensional version of it. So the next step for this, you have to look at action of finite dimensional Lie groups over manifolds and then find the analog of this, and then but the Faddeev-Popov method is infinite dimensional version of that, which is, and then you have to introduce ghosts and anti-ghosts, but then the thing becomes quite transparent that way. All right, so that's it. That's what we need in order to prove this theorem. What happens in our example actually is the following. In our example, this X is going to be the set of one valent labeled graphs with 4K vertices. So again, like K equal to 2. So now that number that I had over there, 1 over K factorial to the power, what was that number? 4 factorial, sorry. 4 factorial to the power K over K factorial. So we had this weight on the left-hand side of this. So 1 over 4 factorial to the power K times K factorial. This is, if you think about it, so imagine you have block of, vertices. Oh, so this is 3, it should not be, I put 4 here because I'm working with 4 valent now. So you have this K of these sets of 4 vertices, or label vertices. And if we complete this, 1, 2, 3, 4, 1, 2, 3, yeah, 4, like that. So basically now this becomes this number is the order of automorphism group of these half edges, because we can switch within each edge, within each set, because there are four of them in each set. So there are 4 factorial, and we have 4 factorial, 4 factorial. So the group has this order 4 factorial to the power k, but then we can also switch globally, because we have these semi edges, blocks of semi edges. And so the order of that group is definitely this. And that's the left-hand side, and that's the summation according to Wick's method. But now we can sum using this orbit summation over a space of orbits, like that. Now, so what is it? So what is the orbits in this case? So you see, orbits are obtained by identifying various graphs under this action of this automorphism group. After you get this, so imagine we have one class, and then we look at the set of automorphisms of that graph. This is exactly this number. So this is this number here. And what is W in this case? The weight is, W is just the Feynman weight. Of the pairing, which is this thing on the left-hand side, or which is Feynman weight of the corresponding graph that you obtain by identifying under this. And everything goes through. There is no problem after having this theorem in mind. There is no problem at all seeing why this is true. Okay, so that's that. Now there is this sticky issue about h bar to the power 2k. I want to relate this 2k to the Euler characteristic of the graph. So let's now. Okay, so let's just look at the definition of, let's record the definition of Euler characteristic. Okay, so what is Euler characteristic of a graph? Well, this is number of vertices minus number of edges, which is, by some very simple homological algebra, this is dimension of h0 of the graph, the number of connected components of the graph, say over R, in this case, h0 over R, minus dimension of h1 gamma over R. So this would be the number of loops, and this is number of connected components. But you don't have to compute homology. You can just go from vertex this one. Okay, now when you look at it, this number for, say, our graphs belong to G. Did I use K-fold? So our graphs have K vertices, and they are 4-valent. So for example, imagine K is equal to 2. They are four valent. Let's take the theta graph, for example. Okay, in this case, you can see that there are four edges. So number of vertices in this case is equal to 2. And number of edges is equal to 4. Okay, so then this guy comes out to be -2. So yeah, so this number for k equal to 2, this number should be the number that's given here is 2k, but the number that I obtained for k equal to 2, I obtained here 4, but here I obtained 2. So basically, this number should be minus Euler characteristic of gamma. So this should be k. I believe this should be k. We derived k equal to, we derived 2k in the last lecture. There must be some mistake there, I think. So I have to check this still. So, yeah, but so, okay, so now let's look at, say, another graph, simple graph, for example, disconnected. Imagine. Yeah, so you have a four-valent thing. So here again, number of vertices v is equal to 2. And in this case, number of edges is again equal to 4. So it's always the same. So you do get, in this simple case, you get h bar to the power negative Euler characteristic. And this root h bar was obtained by change of variable formula. Okay, so basically that's this combinator, this simple group action result, very simple but very fundamental and very, in a way, deep result, gives us reduction from summation using Wick's theorem to summation using Feynman's theorem. Okay, but then we don't have to stop at this sort of simple potentials that or actions that we looked at. We can just move on now and look at more general actions. So in general, so this would be, so far we just looked at one example, right? So now let's look at example 2. So asymptotic expansion for something like this. So okay, so let me not write it again. So imagine s of x again is so imagine s of x is of the following form. We have minus 1/2 x squared minus, not minus, plus, sorry, minus g over 4 factorial. So let's call it g4 over 4 factorial x4. And so minus g3 over 3 factorial x3. Okay. So we have, so now the action is, again, a polynomial, but it has a degree 3 term and degree 4 term, and this is the kinetic energy term, right? Okay, well, then in this case, again, so the summation is over, so this integral, let's call it I, is given by some, now this time, so this time is interesting, so a little more interesting. Gamma belongs to the set of graphs with so let me put it like this: 3, 4, K, L. So this is graphs with with K 4-valent, with K 3-valent vertices and L 4-valent vertices. Okay. So this summation now is over all K and L bigger than or equal to 0. There should be some factor here. Again, this is just H bar half in front. Now, this guy here is, I just put W of gamma, and then we should have H bar to the power minus Euler characteristic of gamma. And then we have to divide by order of automorphism of gamma, like in general. So for each K and L fixed, this set, of course, is a finite set. And what is W? So W is defined in a very similar way. So let's take one of these graphs, for example, something like this now. So imagine you have two trivalent vertices, and you have one 4-valent vertex. Okay. And what do? We just decorate these things by this. In this case, again, everything is very simple. We just put A inverse here, propagators on all edges. And we put G here on vertices. And we multiply all of them. Okay, now this result again, so I mean the proof is completely similar. So you start the proof by writing e to the 1 over h bar s of x as in the following form. So you just say e to the minus 1 over h of bar s of x is equal to, exponential of minus 1 over h bar a x squared. And then we've got some, is a huge sum, K and L. I'm using K and L, yes, from 0 to infinity. And then you just write a product of two exponentials. So exponential of this G4 term and G3 term. So yes, so this becomes G4 x4 divided by 4 factorial to the power k, divided by k factorial times G3 x3 divided by 3 factorial to the power L divided by L factorial. Okay, so we get that, right? Now, the thing is, this number that you get here, 4 factorial to the power k times k factorial. And then we have got here 3 factorial to the power L. Now this 3 has to be inside, to the power 3 factorial to the power L. We are counting denominators now. And then times L factorial. This number is the order of automorphism group But in this case, the automorphisms are obtained by making half edges from so you go like this now this time. Same trick, exactly same trick, but you go now like this. So we have got K vertices, the 4 valent. So we just okay, and then we create a group of 4 of them, K of them. So there are total K of these things, and each K blocks of 4 each, right? And then we have L blocks of 3 each here. This time we get L blocks. Now what we do, we just create these half edges like this. And then here. And here also we do half edges. And now what we are doing, we are making these all possible pairings, just using Wick's theorem, right? So some of these terms can come here, some of them can be connected to this one, like this, and these two, and so on and so forth. So you can connect within this group or within that group. It doesn't matter. So the result of this thing is you get an element, a graph gamma belonging to G. So my notation, I hope I remember 3, 4 KL. You get such a thing. And yeah, so the order, if you think about it, the automorphism group of this gadget is exactly, its order is exactly this number. So this is really left-hand side of the orbit summation. And right-hand side, when you do get the fixed points, I mean, not fixed point, when you reduce to orbits, and then you pick a representative of that orbit, and then you have to still, because you're over counting over that representative if you don't divide by the order of that representative, and that's how you get this right-hand side, which is right there. So, I mean, the point is that this result now works for any polynomial, but you have to write these coefficients. The right normalization is here by 4 factorial, 3 factorial, and so on and so forth. So basically, then what we have is, yeah. So yeah, we can have a theorem. Oh yeah, in this case, actually, the Euler characteristic count is a bit more interesting. So I don't get into that now because I have to check that h bar to the power 2k for myself first before committing myself to something. But basically now you can write down for such actions complete asymptotic expansions minus some, I say GL over L factorial x to the power L, L from 0, say infinity, but infinity really we mean finite. Oh, no, not 0. I don't want to go from 0. Let's go from 3. Yeah. So, yeah, I mean, this we can just write as summation of, yeah, there is some, I mean, the asymptotic expansion of the integral is there is this h bar. So again, there is this h bar to the power negative Euler characteristic of the graph times Feynman weight of the graph divided by order of automorphism group of the graph. But then in this case, gamma belongs to, okay, so a set like this, how to write it, to say N3, N4, N5, so on and so forth. So this guy has N3 3-valent graphs, and 4-valent graphs, etc. That's not bad. So yeah, so let's put it belong to G of this. Yeah, so and this summation is over all numbers, so ni's are bigger than or equal to 0, I bigger than or equal to 3. So it's a sum, it's sum. Okay, so I think yeah, there are several other tricks in this business. So I will recall them. So I mean, for example, one idea is to further reduce by going to connected graphs. Turns out to be log of these things. I mean, so the next idea, but then is what happens if we have some something in front. So what if we want to compute expectation values? In that case, the graphs will get external edges. Those external edges are going to be one-valent and they're going to be labeled, so they don't contribute to the automorphism group of the graph. So this we'll see later on, maybe after holidays.